get started.
Okay.
Welcome everybody to this first Thursday session of SXNS 16, and we have a number of invited talks and contributed talks and also a sponsored talk from XR Nanotech. So we will start with the invited talk from Gary Harlow from Malmö University, and he will report on electron structure movies, high energy surface X-ray diffraction for in situ electrochemistry. And before you start, Gary, one important announcement. After this session, we are going to take a photograph. So please stay in and do not leave immediately for the coffee break. I mean, I will repeat that at least one more time, but already at the beginning, you should be informed about that. And please stick to the schedule and leave some time for questions. And also the audience is strongly encouraged to ask questions. There's even a prize I've seen. Yeah, so especially for the younger audience, take your chance and ask questions. So please, Gary.
Okay, thank you for the introduction. So I'm Gary. I did my PhD in Liverpool. I did postdocs in London, Copenhagen University, and I'm currently a joint project researcher between Malmö University and Nanomax. So today I'm going to talk about high energy surface X-ray diffraction and electrochemistry, and try and show some sort of movies for during in situ data. If you want to contact me, my email address is there. And let's get started. So, no. Okay, so the contents of this talk will be basically why do we care about the surface structure of electrodes, surface X-ray diffraction at higher energies and data extraction, and methanol electrooxidation on gold 111. So there's been various schemes for net emission technologies and green carbon cycles. Basically, you can use various electrochemical technologies and other forms of catalysis to convert things like CO2 into useful products and fuels. And many of these technologies involve electrochemical interfaces, so that can be things like water splitting electrolyzers, fuel cells, CO2 reduction electrolyzers, chemical conversion using electrochemistry, batteries, and also most materials undergo some kind of corrosion. And what we'd like to do is understand these processes on the molecular level. Methanol oxidation is one example, so you can get these sort of direct methanol fuel cells. The advantage of these is they have a higher specific volume density than hydrogen, which is good for automotive applications. And the reaction doesn't involve any CC bond breaking like the higher number of carbon chains. But the main problem associated with this is the so-called dual pathway mechanism, where instead of going, I'll see if I can get the cursor, interruptions. So instead of going the sort of the direct oxidation path, there's an indirect path, especially on platinum surfaces, where you produce CO, and this poisons the surface, and this reduces the efficiency of catalysts. Absorption energies at these interfaces can be strongly structure dependent, so it can really matter what the interface looks like and what the available sites are on how the reaction proceeds. And we can test various different sites using one strategy to do this is to use different single crystal surfaces. So you can imagine that you take a crystal and you cut it in a certain direction, and then you test your chemical reaction on these surfaces, and you see what kind of reactivity or selectivity you get. And then you feed this knowledge back into sort of theory, and you can then use theory to maybe design real catalysts. Of course, this is a massive simplification on reality, but we have to choose some strategy, and this is perhaps one simple strategy or one simple approach. But then I could ask you a question: what is the average structure or the average surface structure of a gold 100 electrode? Does it look like A or does it look like B? And the answer is it depends on the potential. So actually, all the low index surfaces of gold reconstruct, and the reconstructions can be controlled or lifted by the potential. So at some potentials, it might look like A, and at other potentials, it might look like B. So what that suggests is that you need to know the structure during reaction conditions. For that, we need in situ techniques. But how do we measure surface structure in situ? At the atomic scale, there are only really two options. You have surface X-ray diffraction, or you have in situ STM. You can get some information, and quite successfully in some cases, from in situ AFM, TEM, and XAFs. But for single crystal surfaces, these are your two main options. I'm of course going to talk about SXRD, and I think most people here are very, very familiar with that. But essentially, you can measure these crystal truncation rods, and by fitting the profile of these crystal truncation rods, you can determine various changes in the structure of the interface. So things like surface relaxation have a different effect than maybe changing the coverage. And so you can construct models and hopefully extract some useful structural information. And we can use either low energies or high energies. At high energies, you have the advantage that you get this sort of distortion-free image of reciprocal space, and any faceting or rods from nanoparticles are quite easy to identify, and you can quickly measure sort of many CTRs up to a high Q range. You can also penetrate difficult sample environments, and the geometry is simpler because all you have to do once you're aligned is rotate your sample. At the lower energies, you have to move your detector around as well to meet the diffraction condition. Some of the problems, though, are the sensitivity is worse. You have a reduced scattering cross section, and I think some materials are very difficult to measure with high energies. And the data processing, because you typically use large area detectors at high energies, is dramatically increased. And in some sample environments, beam damage can be more of an issue. And then the current dynamic range of detectors is fairly limited. So if you want to measure the weak crystal truncation rod signal between the Bragg spots, you need to put beam stops in the way of the Bragg spots, because otherwise they'll just saturate your signal. And this is a paper of Andreas's, also Uta, and you can see that this shows sort of the curvature of CTRs at various positions on a detector at low energies, and this shows it at high energies. And you can see that at high energies the CTRs are almost straight. So this makes analyzing them and immediately interpreting them a little bit simpler. So for electrochemistry, there are several designs of electrochemical cells around. So you have this kind of hanging droplet where you have a droplet of electrolyte over your electrode. There are various kinds of flow cells one can come up with, or there are thin layer cells where you use some kind of thin film to hold the electrolyte in place over your sample. This is one of the beam lines that we use. This is P. I have to disable this pointer. So this is P21 at DAISY. So this was in December. We had an experiment. You can see this is the beam line. On the diffractometer there is our sample environment. And the beam comes along this flight tube from the optics hutch, and then it hits our sample, which is inside this electrochemical cell. Our electrolyte is being pumped and it's held up there in a tray. And then we have our detector where we have these various beam stops that block out the Bragg spots. Bonus points if anyone could get the structure of that. I don't think so. And then you can see up here we just have a parasortic pump that circulates the electrolyte. So in this case, we use that flow cell arrangement that I talked about. See that up there. Okay. So what does it look like on your detector? As you rotate your sample, the Ewald sphere starts to intercept the crystal truncation rods, and you see intensity moving along up your detector. You can process this in two sort of simple ways. You can average the intensity, or you can take the maximum intensity across the rotation. What you can see is if you take a big rotation, the average intensity quickly becomes saturated by the background. So often I'll present images with the maximum intensity, but you can get the summed or average intensity just by making choosing a smaller angular range. And so what we can then do is we can assign coordinates to these sort of combined images, and immediately sort of get some information about what the structure looks like of our sample. So that in this case, this is a reconstructed gold 111 surface, and you can see rods at the integer spots due to the CTR, and then there's rods just at the side from the surface reconstruction. And this particular representation is independent of the rotation of the sample. So this is essentially your momentum transfer, your QR and QZ. But what does the data that you collect actually look like? Well, you have a stack of images, maybe some background and dark images, and the stack corresponds to each angle in your rotation. And a quick back of the envelope calculation will tell you that if you want sort of a resolution of 0.1 degrees, that's going to be 1,800 images, or about 4.2. So each image is about 4.2 million pixels, and so throughout a rotation, that's about 7.5 billion pixels, or about 15 gigabytes of data for one scan. So it's not inconsiderable. So one of the things that I've been involved in is developing this software. I'll play this movie, and this is called the High Energy Analysis Toolkit. I've skipped some of the loading for you, but basically we can use it to analyze these high energy surface X-ray diffraction data. If you hover over a pixel, you can get the intensity and the position. Now it's loaded. You can change the angular range and sort of explore your data set by scrolling through it here. You can see this is like the scan I showed you before. You can change the color. I just set the angles back to the full range of the scan. And then we can also quickly convert this to this coordinate representation. So this corrects for the curvature of the Ewald sphere, like this. And then what we're able to do is we can add various masks into this. So what we can do is we can select pixels that we're interested in, because one of the problems with this high energy surface X-ray diffraction is you can see everything. You see any powders, and all the horrible things about your sample that you probably don't want to see, or maybe you do. So we can select some various regions that we're interested in. And then in the background, I think it's now going to it's converting this into a reciprocal space map. So you can choose a projection to include those pixels in. And then we have this sort of reciprocal space map. We can take line profiles across this. So this is equivalent of your sort of in-plane scan in normal surface diffraction. And you can sort of really play around with the data and see what you actually have. So this is the higher order reconstruction or the spots around one of the CTRs due to the reconstruction on the gold 111. You can also, if you want to extract CTRs, you can take a mask in the in plane, and then you can actually project that on a on say the H and L plane, and you can use that to extract a. So there I'm changing the projection, and then you can change the view and tell it to bin that again, and it will project that onto the HL plane, and you get something that will look like a CTR. It's coming, I think. And then you could take a profile across the CTR and extract the intensity. So this is actually binning every pixel that's in the mask and putting it in a three-dimensional bin. You get something that looks like a CTR. In this case, it really does need to be background subtracted. Okay. Some examples. So this is an example where we've used it from the ESRF on a platinum 111 sample. And you can see one of the advantages of this high energy surface X-ray diffraction is you can really collect a lot of CTRs. You can get the symmetry equivalents and sort of really normalize your data quite nicely. Here's another recent example which we published where we actually used two detectors, so we could go further out into reciprocal space. So this was iridium dioxide on titanium dioxide. And in this case, we were looking at the stability. So actually not very much was changing, which was good. So back onto this gold surface. So it's well known that the gold surface has this so-called herringbone reconstruction, where you have this transition from FCC to HCP domains, and then you have these stripes that separate this transition. And because you have free rotated domains, you get these shoulders, which give it sort of this typical herringbone pattern. A lead pattern might look something like this. I don't know if this is a particularly good one, but in reciprocal space, you see sort of this hexagonal spots around your CTRs. And there's been a lot of, I mean, it's a bit crazy, really. There's been a lot of surface diffraction studies on this system, and it's become a bit of a benchmark almost for techniques, which is kind of why we're doing it. So, in the early 90s, Alex Sandy and also Ben Occo, they published quite a few papers on this. I published a couple of papers on this. The binoculars software, if you look at the paper that introduces that, they also measure this in electrochemistry. And this is sort of the reciprocal space map that we could get on binoculars. And if we simulate what it should look like, what a reciprocal space pattern should look like, so we have a real space model like this, and we have free rotated domains of this, we get a pattern that looks like this. So at the integer reciprocal space positions, you have your CTRs, and then surrounding them, you have these extra spots which are due to the surface reconstruction. So the different colors represent the different rotational domains. Why is methanol oxidation, or why is this surface interesting for methanol oxidation? Well, one reason might be that there's quite a few studies showing interesting electrocatalytic properties of gold surfaces towards methanol oxidation. So, for example, it's been shown that CO promotes the early partial electrooxidation of methanol. So if you look at your HPLC intensity with CO on the surface, you already get some oxidation of the methanol down at lower potentials. Whereas with just the gold 111 surface, most of the oxidation happens at much higher potentials. Okay, so we collected some in-plane maps. So this shows the the in-plane map at the lower, or the more negative potential, so it's 0.1 volts. This is versus the reversible hydrogen electrode. And you can see that you have these spots around the CTRs due to the surface reconstruction. And if we go to a high potential, and we really have to go to quite a high potential actually, you can lift the reconstruction, and then you just have the CTRs. You can zoom in on some of these reconstruction spots. And in this case, I've used a sort of a Gaussian interpolation just to make it look a little bit nicer, but it's not much worse if you just look at the bind intensity. And so these are two spots, and you can see this hexagonal hexagon around the CTRs. The out of plane pictures look like this. So again, you can see the CTR, and then you can see the reconstruction rod at the side of the CTR. And then if you go to the same potential, you can basically lift the reconstruction, and then you just end up with the CTRs. You can extract the profile of these CTRs. I've done a sort of a quick fit of these. It needs a little bit more work, but basically at the high potential, when we've lifted the CTR, in this case, it looks like a very rough gold surface. So that's why the model's not perfect. I have to play around with some roughness models for this. And then when you have the reconstruction, you get this strong interference effect. And you can see that the intensity dips between the Bragg peaks quite dramatically. We can also do sort of quick scans. So I think I'll play that again. So if we rotate the sample, and then we rotate it back around a small angle, we can see the sort of time evolution as we change the potential. So in this case, the reason that there's some thickness to this line, and I just added an extra image at the end. So the next image that it's collecting, I just made a really bright image, so you can see how it's scanning. The reason that there's a thickness to that is because we're taking intensity in these masks, so up along the Z direction. And so that means that the pixels don't just fall in a neat line; they sort of spread out a little bit. And then we can look at this as we do a CV. I've sort of skipped a little bit ahead because it's not very much happens all the way up here. But this is this current is due to methanol oxidation, and you can see here you have the surface reconstruction rods, and then as we go into methanol oxidation, we can see that the reconstruction starts to lift, but it's still present quite far into methanol oxidation. So it's kind of interesting to know that if you do a first cycle into methanol oxidation, you really do still have the reconstruction to, I don't know, quite far into it. And then when you reverse the potential, it's also interesting to note that you have to go to a much more negative potential to reform the reconstruction. And we're scanning quite slow here. We're scanning at 5 millivolts per second. So ordinarily it would have plenty of time to have recovered by now. And then you can see eventually the surface reconstruction starts to reform at more negative potentials. Okay, but it didn't quite recover fully. We can sort of look at that in this way. So if we simulate what happens when we change the distance between the stripes in this model, we can see that the spots around the CTR move in. So this is a simulated calculation, and that's pretty much what we saw in the real data. So it's sort of this unraveling of the electrode surface. Okay, we can also analyze it in a more sort of conventional way. So we can take a line profile almost through the CTR and the reconstruction. If we add it to get sort of a better signal, and then we can plot that and fit a double Lorentzian, and this has been done in the past quite successfully. we can look at our fits as a function of time. So this is the data. This is the fit, so it matches pretty well. And this is the difference. So there's not very much deviation between our fit to this line profile and actually what we see. And from that we can extract various parameters about our electrode surface. So in this case, we've converted the stripe separation, which is based on the position of the reconstruction peak, into a uniaxial compression of the surface layer versus the sort of normal bulk layer. And what you can see is as you go higher into potential, the surface becomes a little bit more compressed before it lifts, and then it lifts. And this happens so that this matches fairly well with the signal from the CV. And then you could also look at, for instance, the correlation length of the 111 surface. Another example, just to quickly show you, we did this in chloric acid, and so here the reconstruction actually lifts at a much lower potential. So they're both against reversible hydrogen electrodes, so they're corrected for the pH. In this case, you can see that we can repeat and lift the surface, and it recovers quite nicely, which isn't the case with methanol. So in conclusion, the gold 111 reconstruction is present during the initial stages of methanol oxidation. But you have to be aware that the surface really does depend on your cycling history, and you have to go to really negative potentials to reform the surface reconstruction. And the surface gets rougher during this potential regime. So you can see from here that you have a very bright signal in the initial cycles, but it's getting weaker. So you're very quickly roughening your surface if you go to sort of these high potentials. Okay, and I'd like to acknowledge all the people that have been involved in this. So these are the guys that were on the experiment. This is pre-pandemic, so we were all able to sit together. Edwin and Lindsay also, and Andreas and Vedran, and the people at the PO7 beamline at DAISY as well. So thank you for listening. These are the references. You can find the software that I showed here. The latest version isn't actually up, but if you're interested in it, please do contact me. This is my email address. So thank you for listening.